Here's a wild idea. What if the best way to make an AI smarter is to force it to forget things? I know, it sounds completely backward, but today we're diving into a really cool technique in deep learning that does exactly that. It's called Dropout, and it's a surprisingly simple idea that has a massive impact on how we build AI that you can actually trust. So let's set the stage with a question you might have wondered about. How can an AI model get a perfect score on its training data? Totally ace the exam, but then when you put it out in the real world with new data, it just completely falls on its face. Well, that's the exact problem we're going to solve today. All right, to really get this, we first need to talk about the hero of our story, the neural network. Understanding how it works is absolutely key to seeing both its incredible power and its one major weakness. So what is a neural network? Well, at its heart, it's a system that's directly inspired by the architecture of our own brains. Just imagine this huge web of interconnected points, or neurons, that all work together to process information, find patterns, and, make decisions. It's this brain-like structure that lets them learn from just insane amounts of data. Think of data flowing through this network in a few key steps. First up, you have the input layer. That's the front door. It's where the raw data, like all the pixels in a photo, comes in. Then that data travels into the hidden layers, and there can be a ton of these, and this is where the real magic happens. This is where the network does all the heavy lifting to find complex patterns. And finally, everything ends up at the output layer, which gives us the final answer, like saying, yep, that's a cat. But here's the catch. For all its brilliance, this learning process has a hidden flaw. It's a problem that happens when a network actually gets a little too good at its job. It's a phenomenon called overfitting. Overfitting is basically what happens when a model stops learning and starts memorizing. Instead of figuring out the general rules and patterns in the data, it just memorizes every single training example, noise and all. It's the classic difference between actually understanding a subject and just cramming the night before a test. You might pass the test, but you haven't really learned anything. And this comparison right here really gets to the heart of it. On the left, we have our goal. Generalization. That's a model that actually learns the underlying patterns. And because of that, it does great on new data it's never seen before. But on the right, you have overfitting. The model's a one-trick pony. It memorized the training set, so the second it sees something new, it fails. The model becomes brittle, specialized, and pretty much useless. And the consequences of this are huge. An overfit model isn't just a little bit worse, it's often completely unreliable. Its performance is all over the place, which means you can't really use it in the real world. And maybe worst of all, because it's learned all this random noise instead of the actual signal, trying to figure out why it's making its decisions becomes next to impossible. It's a total black box. So what do we do about it? How can we push the model to learn the general rules instead of just cheating by memorizing? Well, the answer lies in a whole category of techniques called regularization. And these are all designed to do one thing: fight overfitting. And this brings us to the star of the show today, one of the most elegant and powerful regularization techniques ever developed. It's a beautiful solution called Dropout. The idea behind Dropout is so simple, but it's incredibly effective. During each step of the training process, we randomly drop, or just temporarily turn off, some of the neurons in a layer. Think of it like a basketball team, where for every single play, a few players are randomly told to sit on the bench. This directly combats a huge problem called co-adaptation, where neurons get lazy and become way too dependent on each other to get the right answer. Okay, so let's walk through what this actually looks like. In step 1, you see our full network, right? All the neurons are active. But then, for one training iteration, that's step 2, we randomly switch a few of them off. They're just gone for a moment. Then, for the very next iteration, step 3, we bring them back, but we switch off a different random set. When you do this over and over, thousands of times, the network can't possibly rely on any one neuron or pathway. It's forced to learn multiple, independent ways to get to the answer, making it way more robust. And the result is captured perfectly in this quote. Dropout forces the network to learn more robust features and reduces dependency on any single neuron. In other words, because no single neuron can be trusted to be there all the time, the team as a whole has to get smarter and more resilient. No one player can carry the team. Everyone has to be able to contribute. And maybe the best thing about this is how easy it is to use in practice. Frameworks you're probably already using, like TensorFlow and PyTorch, have built-in dropout layers. You can literally add it to your model with just a single line of code. A good rule of thumb is to use a dropout rate of about 20% for hidden layers and maybe up to 50% for the bigger layers with lots of parameters. And modern frameworks use a clever trick called inverted dropout, which handles all the math during training, so when it's time to actually use your model for predictions, you can just use the full, complete network without any extra steps. It just works. So it's pretty ironic when you think about it. By forcing our AI to be a little bit forgetful and unreliable during training, we end up with a final model that is way more robust and way more intelligent. So let's just quickly recap the big wins here. First, as we talked about, it prevents that co-adaptation problem, which forces the network to generalize better. This, in turn, makes the entire model way more resilient to noisy or unexpected data. But the coolest benefit is what we call the ensemble effect. Because every training step uses a slightly different, thinned-out network, it's almost like you're training thousands of different, smaller networks all at once and then averaging their results. It's an incredibly efficient way to get a huge boost in performance. And really, that's the whole point of Dropout. It's a direct, powerful attack on overfitting. By forcing the network to be a little forgetful, we guide it away from lazy memorization and push it toward genuine understanding. And the result is an AI that we can actually trust to work not just in the lab, but out in the messy, unpredictable real world. So I'll leave you with this one last thought to chew on. If making an artificial brain randomly forget pieces of what it knows actually makes it smarter and more adaptable in the long run, what does that tell us about the nature of learning itself? Pretty fascinating stuff.